So we're going to do a quick little reminder on how to find the domain and the range of a function. So here are your basic definitions for domain and range. We need to describe all the inputs and all the outputs of a function. And there's different ways that we can describe. We can use words, or we can use inequalities, or we can use lists. So we could use words, inequalities, or lists. Those are our main ways of describing the domain and the range. So the first important thing is that there's two main types of domain and range. We have a discrete domain and range, which is the first example that we're going to cover here. And then we will see moving forward what we call a continuous domain or range. So first and foremost, the discrete domain or range, whatever one we would be looking at, discrete would describe either one of them. That means that we could physically count the number of inputs or outputs. Now if we can count something, that means we could make a list of them. So for instance, I have this graph right here, and I also have this graph prepared over here. So here's the graph of our function, and we can see that I can easily count how many points there are. There's 1, 2, 3, 4, 5 points. There's nothing else, so I can count the input-output pairs. So since I can count them, I could just easily make a list of them. So for this first example, if I was going to list all of the inputs, when I have a graph, really, it might help me say list all the x values on that graph. So if I'm going to list all the x values on that graph, I'm just going to go in order from smallest to biggest. So the first x value on that graph has an x value of -3, and then the next x value is -2. The next point has an x value of -1. Then there's an x value of 0 and an x value of 2. So the only x values that you will see on my graph are these. Same thing with the range. The only y values that you're going to see on my graph are going to be -3. That's the lowest y value down here. The next y value is 1. The next y value is 3. The next y value is 4. And the next y value is 5. There are no other y values on this graph besides these. Now if I have a different representation of a function, so here I just have a mapping, when I'm doing something like this, again, I can easily see that there's 3 inputs and 2 outputs. So I can count them. So for the domain, I'm just going to list all of the inputs. So the inputs over here are going to be the letters A, B, and D. So those are the inputs into the function. Now the things that I can get out of that function, so like if I put in A, I will get out the number 1. So I'm going to add that to my output. If I put in B, I'm going to also get out the number 1. So I don't need to add that to my outputs because it's already there. If I input D, I will get 9. So with that, just as I just went over, there's a few important things to remember. Note, we do not list duplicates in the domain and range. So for example, we saw over here that A and B both went to the output of 1, but we only listed that output once. The last thing that I do want you to note is we traditionally write the domain and range in order, from smallest to biggest. Now we do then lose what pairs with what, but that's okay. Now the next example is a continuous domain and range. Now a continuous domain and range would be something that we cannot count. So in other words, has an infinite number of inputs and outputs. We will look at a graph in a second. What that means, it would look like a connected graph. So a nice solid smooth curve or line. Now because there's an infinite number of something, we cannot list it. So we will need to describe them using an inequality or words. So here's a quick example. We have a function called d of s that gives you the distance traveled given the speed you were going for that hour. So s we can see is our input because it's inside the parentheses of that function. So here's our input value, it's s. So if we were asked for the domain here, we'd have to describe all of the input values. So here the inputs are measuring speed that you could drive. And our thinking here is there are way too many different values of speed to list. Again, the idea is I could go 10 miles an hour, I could go 10.1 miles per hour, I could go 10.01 miles per hour, 10.00, 001. That list would never end. So because there's too many to list, we have to use words to describe them. So that's our thought on that. So if our thought was, well, we have to use words, I'd have to describe what are all the speeds that we could plug in. I would say the speed could be any number bigger than 0. And depending on the car, maybe if I don't know like what type of vehicle I'm in, you might have an upper limit, but right now you just say the speed can only be anything that's bigger than 0. Now the range is the output. Right now, the output here, if we know the speed, it will give us out the distance. So again, there's too many distances that we could ever come up with. I could go 0 miles, I could go 0.1 miles, I could go 0.2 miles. But if I can travel any speed, then I can get any distance out of there. So there's too many to list. So the distance that we will get out are all bigger than 0. Could be equal to 0. Now up here, I could also say it could be equal to 0. But if I'm not traveling anywhere, that we kind of just wouldn't really want to consider that case. So just a general idea. There's too many speeds for me to list. There's too many distances. There's too many values that would make sense. So I can't list them. I have to write them using words. Now more importantly on a graph, when we see a graph, this was our definition that it was a connected graph. It's not just a bunch of dots. If I thought about how many dots were on this line, there'd be way too many of them to list. Because, for example, there's a dot here, there's a dot there. There's an infinite number of dots that make up a connected line. So there's too many dots for me to list. So since I can't list them, I have to describe them using some sort of inequality. Now with this type of graph, what we're going to look for is I can't describe all of the x values because there's way too many of them in this line. All these x values have a point on the graph. And if I go look at that graph, I can see if I trace the values that are here, and I look at the x values, they're just really any decimal in between there. So there's way too many of these points to list. All of these are separate points on our graph here. So what we're going to do is we're going to look for a starting point and an ending point. So it's very clear for me to see if I use just like a vertical line right here. This is that very first x value. If I look at the graph a little more specifically, that very first x value is -2. So here we have the number -2. Same thing, I could look at the very biggest x value, which is clearly right here. And again, on the graph, I have a little better scale here. So I can see on the graph, the biggest x value is +2. So I can't go any past +2 on the x values. I can slide this point anywhere I want and see the x values are all changing. They're getting smaller, but I can't go past -2 on this graph. I get stuck at -2. So what I can see then is the smallest x value is -2. The biggest x value was +2. And again, I can get a little better picture of this graph here. I guess some of it got cut off. Let's get those lines back in there. So our smallest number was a -2. Our smallest x value, excuse me, was -2. Our biggest x value was +2. So we can see a little bit easier. There's -2. There's +2. So if we can describe the biggest and the smallest, then we know, again, just by looking at the graph, every single x value in between there will exist. So here's the smallest at -2. I can pick any number I want, like 1.7. I can find that x value somewhere down here, but I cannot find an x value that's bigger than 2. So all the x's on our graph, we're going to use an inequality. They could be they could be greater than or equal to -2, but they're all less than or equal to +2. So in other words, what we're saying, if you pick any point on my graph, you'll have an x value that's between -2 and 2. So again, I can just go verify that. I just go pick a random point. Here's 1. Its x value is between -2 and 2. Same thing here. It is +2, but it's again in between -2 and 2. With the y values, we do the same thing, but here we want to look for y values, which are outputs, right? So I'm going to go look for my biggest and my smallest output value. So here's the shortest y value. That's down there at -4. And here's the tallest y value, which is here at 8. So what I'm saying is if I look at my graph and now I'm just looking at the y values, I can find any y value, but I can't find a y value that's bigger than 8. This is the top of the graph, so I can't go past 8 on the y-axis. But then all these other points down here, just any kind of y value I want, but I can't go below -4. So I found the lowest y value at -4. And the biggest y value at 8, and since my graph is smooth and connected, every other y value exists in between there. So again, what I can say is I can find my lowest value is -4, my tallest y value is 8, and every single y value on the graph will be bigger than -4 or equal to it, or it's going to be less than or equal to -8. So as a sentence, any point we choose on the graph will have a y value between -4 and 8. And of course it could be -4 and it could be 8. Let's go look at another example. So here again we can see that there's way too many x values to list. So what I'm going to do is I'm just going to look at all these points and say, well, let's look at all the x values. What is the smallest x value I can find and what's the biggest x value? And I'm seeing that it's just really any number, but I can't go past -3 on this side, so my smallest x value is -3. And over here, I can't go past +3. So like on my graph, what I could easily show is the smallest x value is -3. The biggest x value is +3, so my x's were all in between -3 and +3. So they're all less than or equal to 3, and they're all bigger than or equal to -3. So in other words, no matter what point I choose on my graph, the x value between -3 and +3. So again, just watch these x values. They're somewhere between -3 and +3. Now with the y values, I can see my tallest point over here is 9. So the y values are going down from 9. This looks like the lowest point. So here it's at 0. And then after that, it starts coming up again. So I could see on my y-axis, I can't go above 9 and I can't get below 0. 0 is going to be my lowest point. So on the graph here, we just kind of indicate our work saying the lowest point is 0 and the biggest point is 9. So all of my y values are between 0 and 9. So in other words, as a sentence, if you pick a point on my graph, the y value is guaranteed to be between 0 and 9. Could be 0 or it could be 9. The last example here, again, there's way too many points to list, so we're going to have to use an inequality because this is a smooth connected graph. The first x value is right there at -7, and the last one's at 0. So my domain should be between -7 and 0 for all of the x values. So if you pick a point on my graph, the x value will not be less than -7, and it won't be bigger than 0. If we go look at that pretty quickly here, we can see that if I slide this, I can't get past -7 on the y-axis, or excuse me, on the x-axis, and I can't get my x value to be bigger than 0. If we look at the y values, the smallest one is -4, and as I keep going, I can go up to like 0, or sorry, up to 1, and then over here I just go to -1. So the lowest y value I can find is right here, that's -4. The tallest I'll ever get is right there at 1. So our range, if we kind of show our work here, the smallest value was at -4. The tallest value was at 1. So our range would go between -4 and 1.